Hi, everybody. Welcome back to Dave's Math channel. This is my new feature on daily math problems, which I've been posting on the Facebook group Classical Mathematics. And, I guess I skipped a couple. This one I should have done a few days ago. Actually, I posted another video on this feature, the more recent, that corresponds to a more recent problem. I've done two problems since this one, so I should have done this a few days ago, but I guess I got a little bit behind. But anyway, in this video, I'm gonna talk about how to solve a particular problem involving finding the two intersection points of an ellipse and a line. Anyway, let's begin. So, in particular, the problem is asking for the two intersection points of the line given by the equation y equals 2 times x plus 1 and the ellipse given by the equation x squared plus xy plus y squared equals 1. Anyway, I showed a graph here. I did this in Mathematica. It's pretty easy to graph lines and ellipses, and you can sort of visually see what the solutions are, but you can't actually solve them just by estimating where the points are. I think it's pretty clear that one of these points is the point minus 1 comma 0, which you can easily check, but the other one, the coordinates aren't so obvious. Anyway, so we really want to solve this problem analytically. And it's really not hard to do. All you do is you substitute the equation for y given by the linear equation, y equals 2 times x plus 1. Substitute that in the equation of the ellipse, and that'll give you the values of x corresponding to the, um, the intersection point. So let's do that. So this is just algebraic manipulation. I'm not going to go through all the steps, but when you're done, you're left with a quadratic equation of x, specifically the equation 7x squared plus 10x plus 3 equals 0. And I think you guys all learned the quadratic formula in high school. You just apply that to this quadratic equation to solve for the roots. And when you do the algebra, you get two roots as you usually do. The two roots are x equals minus 1 and x equals minus 3/7. Well, x equals minus 1 is kind of the obvious root. That's correspond to the point minus 1 comma 0. But the other one is more complicated. Anyway, it's pretty easy to solve for y once you get x. You just back substitute. You're using the equation we had for y of x, which is y equals 2 times x plus 1. So for instance, y corresponding to x equals minus 1 is 2 times negative 1 plus 1, or 2 times 0 or 0. That's what we expect. That gives you the point negative 1 comma 0. And then the other value of x we found, namely x equals minus 3/7. When you do the algebra, you get 8/7 for y. So you get the second point is the point minus 3/7 comma 8/7. I think you can sort of see it from the graph. Let me go back to the graph here. I don't know if you can see the hash marks for x and y. I think you can see that the value of x is around minus a half, a little less than minus a half, 3/7, a little less than minus a half. And then the value of y is a little bigger than 1, because 1 is the value of y where the ellipse intersects the y-axis, and it's a little higher than that. So it's a little bigger than 1, it's 8/7. So it sort of checks with a graph, which is kind of a sanity check of our solution. So that's the answer. That's the answer to the problem. But before I get off of this problem, I think I want to point out something really interesting here. There was no reason we had to use the slope 2 for the line. I mean, it is nice to start with a line of the form y equals t times x plus 1, where t is an arbitrary real number. That just gives you a line of arbitrary slope passing through the point negative 1 comma 0. So you know that one of the points is going to be minus 1 comma 0, but the other point depends on t. And what's nice about this problem is that if t is rational, well, it doesn't even have to be rational. If t is any real number, you always get 2 points. You always get a second point, and you can solve for it with exactly the same method we used here. It's just that this time we saw substitute y equals t times x plus 1 instead of y equals 2 times x plus 1. And I'm not giving all the steps here. You can check this yourself, but it turns out if you do the algebra, the second point you get is this kind of ugly looking point. The x coordinate is 1 minus t squared over 1 plus t squared. And the y coordinate is t times 2 plus t with the same denominator, 1 plus t squared. You can check that for yourself. You can also check that when t equals 2, you get the solution we found earlier, negative 3/7, comma 8/7. And what I think is really nice about this problem is that if you let t be a rational number, say t equals m over n, then you can actually get a parameterization of all rational solutions, all rational points on the ellipse that we started with. I'm not going to go through the details here, but actually, I mean, we already know what the answer is. That if t is m over n, and you can simplify it in terms of m and n if you like. I guess you would get n squared minus m squared over m squared plus mn plus n squared for x, and then for y you get what m over n. I'm trying to simplify this out. M times m plus n over the same thing, m squared plus mn plus n squared. And that actually gives you a solution to the Diophantine equation, a squared plus ab plus b squared equals c squared. We just let c squared be m squared plus mn plus n squared. And you can do something exactly like this to find all primitive Pythagorean triples. In that case, you would just use the unit circle instead of, x squared plus y squared equals 1, instead of this funny ellipse we're using here. But, the same method will give you a parameterization of every rational point on this ellipse. And it didn't have to be this particular ellipse. It could have been, any conic, it turns out. Then you have to be an ellipse, but any conic section. You take one fixed point on it, one fixed rational point, and then you give a line of arbitrary rational slope, and then you're always going to get a second intersection point which you can parameterize. Very nice method. Anyway, I just thought I'd point that out. So anyway, that completes my video for today. Yeah, so thank you for watching. Long live math, and I'll see you guys next time. Bye.